Welcome back. Today we're diving into why temperature and altitude are crucial for every pilot, from student to airline captain. It's not just about checking the weather app. These two factors shape how your aircraft performs, how much fuel you burn, and where you'll find the smoothest air. Think of temperature and altitude as your invisible co-pilots, always giving you clues about the atmosphere. Ignore them, and you're flying blind. This is why your plane rockets skyward on a cold morning but struggles on a hot afternoon. It's also the secret to avoiding icing and finding the most efficient cruising altitude. Airliners don't pick 35,000 feet at random. They're hunting for the sweet spot where engines are most efficient and the ride is smoothest. Mastering this concept early makes you a smarter, safer pilot. So grab your notebook. We're about to uncover the secrets of temperature and altitude. Let's get started. Let's embark on a journey to understand the Earth's weather factory, starting with the troposphere, the atmospheric layer closest to us. It's where all the action happens, the stage for our daily weather dramas. This is the lowest layer of the atmosphere, the very air we breathe, and where all our weather, from gentle breezes to raging storms, is born and plays out. It's a dynamic and ever-changing environment. It stretches up to about 36,000 feet, or roughly 7 miles, and is where commercial pilots spend most of their time navigating the skies. It's the layer that directly impacts our lives. The key rule to remember here is that as you climb higher within the troposphere, the temperature consistently gets colder. This is a fundamental principle that governs weather patterns. The sun, our primary energy source, heats the ground, which in turn warms the air directly near the Earth's surface. This creates a temperature gradient. The higher you go, the further you are from that initial heat source radiating from the ground. This distance plays a crucial role in the temperature drop we experience with altitude. In aviation and meteorology in general, we use what's called the standard lapse rate. This is a rule of thumb. The temperature drops approximately 2 degrees Celsius or 3.6 degrees Fahrenheit for every 1,000 feet you climb. So, as a quick example, if it's a pleasant 15 degrees Celsius on the ground, you can reasonably expect it to be around -5 degrees Celsius at 10,000 feet above ground level. This understanding of temperature change with altitude helps you predict the freezing level, a critical piece of information for pilots to avoid potentially dangerous icing conditions on aircraft. However, keep in mind that sometimes the temperature drops faster or slower than the standard rate. This is known as the actual lapse rate, and it's constantly changing based on prevailing weather conditions. A steep lapse rate, where the temperature drops rapidly with altitude, generally indicates unstable air, which can lead to turbulence and bumpy conditions. Conversely, a shallow lapse rate, where the temperature changes slowly with altitude, suggests smoother, more stable atmospheric conditions and a more comfortable flight. Understanding the lapse rate, both standard and actual, helps you anticipate the kind of ride you'll have, allowing for better flight planning and decision-making. Grasping these concepts is the first crucial step towards reading the sky like a seasoned professional, enabling you to make informed judgments about weather and its impact on your activities. As you climb, you'll eventually reach a point where the temperature stops dropping, the tropopause. This is the boundary between the turbulent troposphere and the calm stratosphere above. The tropopause acts like a lid on weather. Most clouds and storms can't break through it. That's why thunderstorm tops flatten into anvils. They've hit the ceiling. For pilots, flying near or above the tropopause often means smoother, safer air. The tropopause's altitude varies, lower over the poles, higher over the equator. It's also where you'll find the jet stream, a fast-moving river of air that can help or hinder your flight. Catching a tailwind here can save time and fuel. A headwind can slow you down. Knowing where the tropopause is helps you pick the best cruising altitude. It's a key to efficient, comfortable flying. Find this boundary, and you unlock the secrets of high-altitude flight. Climb above the tropopause into the stratosphere, and the rules flip. The higher you go, the warmer it gets. This is due to the ozone layer, which absorbs the sun's UV rays and heats the surrounding air. The result? A temperature inversion: warm air sits above cooler air, creating a very stable layer. There's little vertical movement, so no clouds, storms, or turbulence. That's why high-altitude aircraft and weather balloons love the stratosphere. Most airliners cruise just below or at the tropopause, right on the edge of this calm layer. Knowing about the stratosphere explains why weather is kept below and why the sky is layered, not uniform. Each layer has its own rules. Understanding them is key to safe flight. The stratosphere completes the picture of how temperature changes from ground to the edge of space. It's the final piece in the atmosphere puzzle for pilots. This isn't just abstract theory confined to textbooks and classrooms. It's not just about memorizing facts and figures. Pilots use this knowledge, this deep understanding of atmospheric principles and aircraft performance, on every single flight they undertake. It's the foundation upon which safe and efficient flight operations are built. Cold air is dense, meaning there are more air molecules packed into a given volume. This increased density has a direct impact on engine and wing performance, leading to improved efficiency. Conversely, hot, thin air means longer takeoff rolls are required, and climb rates are significantly reduced. The aircraft simply doesn't generate as much lift or thrust in these conditions. Therefore, it's crucial to always check performance charts before takeoff, paying particular attention to temperature, altitude, and runway length, especially on hot days when performance margins are reduced. Predicting the freezing level, the altitude at which the temperature drops to 0 degrees Celsius, is essential to avoid potentially hazardous icing conditions. As a general rule of thumb, if it's 10 degrees Celsius on the ground, expect freezing temperatures at approximately 5,000 feet above ground level. This is a critical piece of information for flight planning. Plan your route strategically to minimize the amount of time spent in areas where icing is likely to occur, such as clouds at or near the freezing level. For efficient fuel planning, remember that jet engines operate most efficiently at high, cold altitudes. This is due to the reduced air density, which translates to less drag and improved overall performance. Before and during a flight, pilots meticulously analyze temperature and wind charts to identify the most favorable cruising altitude, taking into account both fuel efficiency and potential tailwinds. Sometimes, making a small altitude adjustment of just a few thousand feet can result in significant fuel savings by taking advantage of favorable wind conditions or temperature gradients. The tropopause, the boundary between the troposphere and the stratosphere, often marks a distinct transition between turbulent air below and smoother air above. If conditions permit and passenger comfort is a priority, climbing above the tropopause can provide a smoother and more enjoyable flight experience. A comprehensive understanding of these atmospheric layers and their characteristics empowers you to make informed, smart, and safe decisions in real time, adapting to changing conditions as they arise. Ultimately, it's about skillfully using scientific principles and meteorological knowledge to effectively manage your flight environment and ensure a safe and efficient journey. And that's precisely what separates a good pilot, who simply follows procedures, from a truly great one, who understands the underlying science and makes informed decisions based on that knowledge. Let's wrap up this section with some practical tips and tricks that you can start using right away. These aren't just abstract concepts, they're tools you can apply in the cockpit to enhance your situational awareness and decision-making. These tips are specifically tailored for student pilots, designed to bridge the gap between theoretical knowledge and real-world application. Make the standard laps rate your go-to tool. It's a fundamental concept that will help you understand how temperature changes with altitude. Specifically, subtract 2 degrees Celsius for every 1,000 feet you climb to estimate temperature aloft. This simple calculation can provide valuable insights into potential weather conditions at different altitudes. Compare this estimated temperature with winds and temperatures aloft, forecasts from your weather briefing. This comparison will help you anticipate freezing levels, potential icing conditions, and any performance issues that might arise due to temperature variations. Understanding these factors is crucial for safe flight planning. Think of air density like swimming. It's all about how easily you can move through the medium. In cold, dense air, it's easy to push off in. Your aircraft will perform better, with increased lift and engine efficiency. Conversely, hot, thin air is sluggish, reducing your aircraft's performance capabilities. Therefore, always calculate density altitude, especially before takeoff. This is especially critical at high elevation airports on hot days, where density altitude can significantly impact your aircraft's ability to take off safely. Always use freezing level charts in your weather briefing. They provide a clear picture of where the freezing level is located along your route. And remember, if your route is near the freezing level and there's moisture present, seriously reconsider your plan. The risk of icing is significantly increased in these conditions. Never underestimate icing. Even a small amount of ice can drastically reduce lift and increase drag. It can quickly become dangerous, leading to loss of control and potentially catastrophic consequences. Pay attention to how the air feels as you climb. Your body can be a valuable sensor. Is the air bumpier or smoother than you anticipated? This can indicate changes in atmospheric stability. Is the temperature dropping as expected according to the standard lapse rate? Deviations could signal unexpected weather phenomena. Notice how cumulus clouds top out at certain altitudes. This is a visual cue that can tell you a lot about the stability of the atmosphere. That's the atmosphere's structure in action, demonstrating how temperature and altitude interact to create different weather patterns. Build your intuition by actively connecting what you feel and observe with what you know from your training and weather briefings. This is the kind of proactive airmanship that keeps you safe, allowing you to anticipate and react to changing conditions effectively. Practice these habits diligently, and you'll not only fly safer, but also smarter every time you take to the skies. Let's review the essentials. Temperature drops about 2 degrees Celsius per 1,000 feet in the troposphere. This rule shapes performance, weather, and safety. Knowing this lets you predict climb performance, freezing levels, and the best cruising altitude. The tropopause caps most weather and marks the start of smoother air. The stratosphere above gets warmer, creating a stable, turbulence-free zone. Internalize these concepts to build real airmanship. Always use your charts, respect density, altitude, and have a plan for icing. This knowledge keeps you and your passengers safe and helps you make smart decisions. Next time you fly, remember the dance between altitude and temperature. It's your key to a safe, efficient flight. Fly safe, and see you next time.